Hello, we're going to continue now our discussion of organic bases. Remember that the Bronsted-Lowry definition of a base. Bronsted-Lowry definition of a base is a proton, which is just H+, acceptor. So something that's a proton acceptor generally has a lone pair of electrons and or a negative charge. So something with a lone pair of electrons and or a negative charge is often attracted to an H+. And our goal right now is to figure out, well, if you have two bases, which one wants the H+ more? So let's look at this example. Which of these bases is stronger? Now we're going to have to do the formal charge on this carbon, and hopefully you can convince yourself that it's -1. There's a lone pair here. And that this nitrogen with two lone pairs has a -1 charge as well. So make sure that you can go back and figure that out. So we want to know, if you had an H+ and you put it into a solution that contained the amide anion, that's what this is called, and a solution, the same solution contained what's called the acetylide anion, so these are the two bases, and you throw an H+ in there, where would it go? Would it go to the amide or would it go to the acetylide? Whichever one it goes to is stronger. It wants it more. And the way we're going to answer this question to decide which base is stronger right now, there is a second way to do this, which we'll get to later. But right now, what we're going to do to answer it is we're going to look at the conjugate, sorry, this is an O, at the conjugate acids. So that's how we're going to answer this question. We're going to look at the conjugate acids of these and determine which one gives the stronger base. So let's go through the process. So what we're going to do is get the conjugate acid of the acetylide, and the conjugate acid is simply made by adding H+. So the H+ goes to that lone pair, which is now this bond right here, and the charges cancel each other. So this is the conjugate acid. And that's called acetylene. Now again, what you could think about is that conjugate acid could lose that proton and form the conjugate base. Now let's compare that to the amide anion. So let's draw out the conjugate acid of this. So we're looking at the conjugate acids. So if we make the conjugate acid, we'll simply add H+ to it, which leaves one lone pair. The charges cancel, so it's neutral, and this is ammonia. So this is the conjugate acid. Of amide. And again, you could think about that as losing H+. So it's going to act as an acid, so lose H+. Oops, sorry. So here we have the two conjugate acids and the conjugate bases they form when you lose H+. So we're really asking which of these wants H+ more. Which one will form the conjugate acid more easily? So we're going to look at the pKa's of the conjugate acids. And if you go to your pKa table that I handed out, the pKa of acetylene is 25. Make sure you can find that. The pKa of ammonia is 33. Well, since the pKa of ammonia is higher than the pKa of acetylene, this is the weaker acid. So this ammonia is weaker. It gives up its proton less easily than acetylene. Now here's the important concept. Because this is the weaker acid, it gives up its proton less easily. This is the stronger base. It wants the proton more because it comes from a weaker acid. So this, therefore, the amide is the stronger base. So the whole concept is, if I want to know what base is stronger, draw out the pKa's, or draw out the conjugate acids, get their pKa's. Whichever one is the weaker acid, higher pKa, gives the stronger conjugate base. So make sure you can understand that concept. Now I did say there's a second way to determine which is stronger, which we'll get to a little later. We just looked at an example. Ammonia is really a type of amine. Amine basically means it's a nitrogen-containing compound. So for example, let's look at a common amine. This is called methylamine. This is a methyl group right here, and this is what makes it an amine. Now clearly, I think you guys could see, hey, there's a lone pair here. This is a potential base. It could abstract, it's attracted to a proton. The question though is, could it act as an acid? In other words, could this give up a proton? Instead of accepting a proton and acting as a base, could it give up a proton? So in other words, could it do this? This is really the question you're asking yourself. Oops, just one H now. So this is nothing because we lost the H+. Okay, so this is the acid. It's acting as an acid right now. Okay, just so you know, it's acting as an acid because it's giving up proton. Now I want to know, how easy does it do that? Well, according to this, it's very unlikely. Why? Because it has a very high pKa. The pKa, and you can look this up, of methylamine is 40. This is a very weak base. Sorry, very weak acid. What that means is, therefore, this compound the anion is a very strong base. So this compound is a very strong base. So just again, let's step back. This can act as a base. That means it could accept a proton. In other words, this would have an H, and it would be NH3+. That's pretty common because it has a lone pair. But I'm saying, could an amine act as an acid? Could it give up a proton and form this base? And the answer is that's very unlikely because this is such a weak acid. The pKa is 40. It's very unlikely to give up a proton. If it did give it up and form this, this is a very strong base because it comes from such a weak acid. So make sure you can get that concept down. I know sometimes you have to think about it for a little bit. The second thing I want to talk about, which is a little more straightforward, is let's say you have an acid-base reaction. And I want to know which way the equilibrium lies. In other words, what's the direction the reaction lies in? That's what I really want to determine. And that's pretty easy. As a general rule, acid-base reactions favor the formation of the weaker acid and the weaker base. Now in this case, weaker equates to more stable. A weaker acid is very likely to hang on to its proton. It's quite stable. It doesn't want to give it up. So a weak acid is very stable. A weak base means that it does not want a proton very much, and it's fairly stable, just hanging out as it is. So many, as we learned in Gen Chem, many reactions under what's called thermodynamic control, which generally means you're going to try to form the more stable species. So when you look at a chemical reaction and try to decide which way the equilibrium lies, it lies toward the more stable species, the weaker species, so to speak. So therefore, the more stable species is favored in an acid-base reaction. That is, the weaker acid and weaker base side of the reaction is favored. So let's take an example of that. Let's draw out this potential base, which is called the acetate anion. Now we know this is a potential base because of the negative charge in the lone pairs, so this could abstract a proton. It has an attraction. So this is our base. Now often with these, you just don't buy the anion. It usually comes when you buy it with a counter cation. Well, in this case I'll put sodium. Often we don't show the counter cation, but I want to do that now for the sake of completeness. So you'd find this is called sodium acetate. Okay, so you have this base with the negative charge on the oxygen, and you throw in an acid. In this case, we're going to throw in hydrogen cyanide. So this is our acid. And there's a triple bond here between the C and the N. Okay, so you put an acid in the base, and what can happen is there's an attraction. There's a sort of a battle for this proton. Right now the cyanide has the proton, but the oxygen is also attracted to this. So potentially what could happen is the lone pair on the oxygen could abstract this proton, and the pair of electrons that was made of that bond will now go dump onto this carbon. So these two electrons now dump onto the carbon, and what could potentially happen then is so this lone pair just became that bond. We abstracted the proton, and now the electrons here are dumped onto the carbon. And the carbon has a negative formal charge. And the sodium countercation would now be with the cyanide. So take a moment and look that over. So on this side we have the base. We just formed the conjugate acid by adding the H+. This side we had the acid. It lost the proton. We formed the conjugate base. So the question is, well, which way does this reaction lie? Was this able to abstract the proton from hydrogen, or did the cyanide from the cyanide, or did the cyanide tend to hang on to it? To answer the question, we're going to look for the more stable species on each side. And it's easiest to focus in on the acids on each side, because we can just look up the pKa's. So the pKa of hydrogen cyanide is 9.1, and you can look that up on the sheet. And the pK of this, which is called acetic acid, is equal to 4.8. Okay, so the reactions lie toward the weaker acid, the more stable acid. This is the weaker acid. So this is the weaker acid. So the reaction lies to the left. It lies toward the weaker acid. And let's see if that makes sense. This acid is weaker than this acid. That means it does not want to give up its proton as readily. So the reaction lies toward the side where it has the proton, which is this left side of the reaction. So we're always the easiest way to tell which way an equilibrium lies is to look whichever has the weaker acid, or you could use the weaker bases, but since we can just look up the pKa's here, it's really easy to look up these and say, hey, the hydrogen cyanide is a weaker acid, and acetic acid, therefore the reaction lies toward that weaker acid. So I will probably send out an email or some way of telling you what I want you to do to turn in a class next time after watching this video.